Okay, today we're going to talk about trigonometric substitutions, and here are the items that you will need for today. You will need this trigonometric substitution reference triangle sheet. Now, this was actually taken from a different textbook, and in my opinion, it's a better layout as to the layout that's actually the e-textbook. Okay, here we're given the three what are called reference triangles, and we're going to need these in what we're going to do today. So you're going to need these trigonometric right triangles. You will also need the trigonometry formula sheet, okay, because I want you to see where a couple of these things are coming from. You also need the basic integration table, and there were a couple of formulas that we added to this, okay, and I'll kind of go through those. And you'll also need the trig derivative sheet. All right, so you're going to need those 4 items. And before we begin, I want to review just some right triangle trigonometry. So just as far as a right triangle is concerned, in a right triangle, right, we must have a right angle, and this right triangle consists of a hypotenuse, and that hypotenuse is always the opposite the right angle, and it's always along its side. And then we have 2 legs. Right. We can use the Pythagorean Theorem to find the hypotenuse or either a leg. So here are the formulas. The hypotenuse squared is equal to the leg squared plus another leg squared. Okay, that's no more than the Pythagorean Theorem. If I were to find the hypotenuse, not the hypotenuse square, I would take the square root of both sides. So out pops this formula. Right, the hypotenuse equals the sum of the legs squared. Right, so on the onset, if I'm looking at a plus, notice that this square root of a leg squared plus a leg squared is actually the dimensions for my hypotenuse. And if I were asked to write out the formula to find the length of a leg, the leg would equal to the square root of the hypotenuse squared minus the leg squared. All right, so notice that the hypotenuse is always along the side. Right, and notice that in this formula, there's actually a minus. So if I'm looking at a minus, right, I have a square root. My first term is a perfect square. My last term is a perfect square. Right, this would give me the length of a leg. All right. Also, some forms we talked about, and these were just facts. And you may want to write these on your formula sheet. The integral for sine square u du. So notice I'm kind of changing my variable so it fits the formula sheet. I'm using a u variable. That was equal to 1/2 u minus 1/4 times the sine of 2u plus c. Right, and we worked that out in the last class. I'm going to write this a slightly different way. This can also be written as 1/2 times the quantity u minus the sine of 2u over 2 plus c. All right, so notice if I distribute 1/2 times u is 1/2 u, 1/2 times negative sine 2u over u is negative 1/4 sine 2u plus c. Okay, I'm just kind of writing in a more compact form Okay, and you're going to see why as we kind of go through the example today. The integral for cosine square u du. This is 1/2 u plus 1/4 times the sine of 2u plus c. I can also write this in a compact form as 1/2 times the quantity u plus the sine of 2u over 2 plus c. Okay. And the last, well, it's actually two more formulas. This is the last one we worked out, the integral for tangent square u. So remember, we had to make a trig substitution for all of these, and we substituted the tangent as 1 plus secant square, right? Or 1 minus secant square. Excuse me, secant square minus 1. We made that trig substitution using the Pythagorean Theorem. So we found this was equal to the tangent of u minus u plus c. And here's another formula I want you to add to your formula sheet. The integral of secant u du. So if you look on that formula sheet, there isn't a formula for the integral of secant, but the integral of secant u du, that's equal to the natural log of the absolute value of secant u plus tangent u plus the arbitrary constant. All right, so here are 4 formulas that you want to add to your formula sheet. All right, and then last, this is just a warm up for the trig we're going to be using today. So here again, this is a right triangle. Okay, I'm going to give this one a reference angle. I'm going to give this a reference angle theta, and I'm going to simply call this x, y, and r. So remember, when we're setting up a trig function, you may hear me say this, so I just want to make sure that we're all on the same page. I may mention Chief Sakatoa. Okay, I don't know if you ever heard of this before, but this little mnemonic saying gives me the 3 trig functions on how to set them up. So, okay, I have x, y, and r, but this kind of relates to opposites, hypotenuse, and adjacents. So just kind of going through this, if I were to use this as my reference angle, and I'm going to label my sides as hypotenuse, opposites, or adjacent. First thing I'll do is label my hypotenuse, right? That's always opposite my right angle. So R is actually my hypotenuse. The side that's opposite my angle, that is the side opposite. And I have my adjacent side. So when we're setting up our trig functions using Chief Sakatoa, the Sakatoa alludes to the side part in this means that the sine of some angle, of our angle, that's equal to the opposite over the hypotenuse. The cosine from Chief Sakatoa alludes to the fact that the cosine is the adjacent over the hypotenuse. And the Toa part of Chief Sakatoa alludes to the fact that the tangent is the opposite over the adjacent. All right, and next we have our reciprocals. The reciprocal for sine is cosecant. So I'm going to reciprocate my fraction, so that's r over y. The reciprocal for cosine is secant. So I'm going to reciprocate. This is r over x. The reciprocal for tangent is cotangent, and this is x over y, right? Or the adjacent over the opposite. All right, so that was just a little right triangle warm up, and also some formulas you should add to your formula sheet. All right, so now I'm gonna share the desktop screen. Okay, and we're gonna look at this trig substitution, reference angle sheet, and it reads that the trig substitutions occur when we replace the variable of integration by a trig function, right? And here are the most common substitutions. We try to substitute the variable for either a tangent, a sine, or a secant. Okay, so notice the three right triangles, and these are right triangles. From what we kind of just described, right, this is our right angle, and this square root of a squared plus x squared would serve as my hypotenuse. I have my reference angle theta. Notice that in my square root, my radicand, my first term would have to be a perfect square, right? And notice that's the length of one of my legs. My second term is also a perfect square, but it's variable, and that's my other leg, which is x. So if this is my setup, right, if this is what I'm given, a squared, the square root of a squared plus x squared, this is my reference triangle. And I can pull out the following facts. X is equal to a times the tangent of theta. The square root of a squared plus x squared is equal to a times the absolute value of secant theta. For my next reference triangle, notice that we have the square root of a squared minus x squared, and it serves as the length of one of the legs, right? So notice that I have the general form for the Pythagorean Theorem, which is a square root. The first term is a perfect square, the last term is a perfect square, and I have my minus, right, which alludes to a leg. Notice in this third reference triangle, we also have the same setup. Okay, the first term is a perfect square, it's variable. The last term is a perfect square, and I have my minus, which alludes to having a leg. Right, so if I go back to the second triangle, I can use this trig substitution. I can substitute x for a times the sine of theta. The square root of a squared minus x squared is equal to a times the absolute value for the cosine of theta. Right, and for our last setup, notice that the square root of a squared minus a squared is the length of a leg. In this case, x serves as the hypotenuse and a serves as my second leg length. I can then use the following relationship. X is equal to a times secant of theta, and the square root of x squared minus a squared is equal to a times the absolute value for the tangent of theta. Now, the reason why the triangles are important are because it's twofold. First, the triangle is important because based on what we're given, we'll be given some type of square root, okay, with two terms. One of the terms would be a perfect square constant. The other would be some type of perfect square variable x. We can choose our reference triangle, and we can make the following substitutions to simplify our integral. We can integrate, and then we use these triangles for back substitution. All right, so let's see how this all works in a couple of problems. All right, so here's the first problem we're going to take a look at. We're asked to integrate the integral for dx divided by the square root of 4 plus x squared. So now you'll result to the trig substitution once you have deduced down to trig substitution. So you wouldn't necessarily automatically jump to trig substitution unless you could, let's say, substitute. So first I would try to substitute, right? Normally we substitute out the innermost function, so I would make this a substitution. And if I take the derivative, I'm left with some kind of x, right, which I can't substitute out. I can't use integration by parts because it's not an actual product. I can't use anything else, but notice the form of the denominator. It's in a hypotenuse type setup. I have a square root. I have my first term, which is 4, which is a perfect square, and I have my second term, which is a perfect square, and its variable x squared. Okay. So now there's going to be 4 steps to actually solve this. Right. The first thing I'm going to do is choose a reference triangle . And we're going to sketch it out. And we're also going to calculate the differential, which is dx. Okay. So just like in the other problems, the substitution problems, we try to rewrite everything. We try to transform the variable. Right? Once we transform the variable, we can integrate, and then we back substitute. So it's basically the same principles here. So the first thing I'm going to do is choose a reference triangle based on those 3 triangles, and we're going to sketch it out. All right, so I actually have this on another sheet of paper. So if I look at my, and that's not readily visible. All right, so if we look at our 3 triangles, which triangle would we choose? Right, well, we're going to choose this first triangle simply because it fits our form. We have the square root of a constant squared, which our constant is 4, or an a would be 2, right? 2 squared is 4, plus we have a plus in our radicand, x squared. So I'm going to choose this first reference triangle. Now I'm going to sketch that out. So here again, I have attached this as a file, and you should be able to download it to your computer. Okay, now I'm back. Okay, so I'm going to sketch this out. So my hypotenuse should actually be 4, the square root of 4 plus x squared. The length of this leg should be a, right, according to our triangle setup. But notice that A is actually 2 because 2 squared is 4. So the length of this leg is 2. And the length of this leg is our variable x. Right? So our intent is to substitute x for some type of trig function. All right, so what is that trig function? Well, if you look back at your triangle, x was equal to a times the tangent of theta. So for our triangle, x is going to equal to a, which is 2 times the tangent of theta. Right, and that was given from our reference triangle. It also says that the square root of a squared plus x squared is equal to a times the absolute value for the secant of theta. So I'm going to write that out as well. I'm going to write the square root of 4 plus x squared as 2 times the absolute value of secant theta. So notice that I'm transforming my variable from x to theta. In the other problems, when we substitute it, we transform the variable from whatever we were given to u. For the trig substitution problems, we are transforming our variable to theta. So this will allow us to rewrite the denominator, right? We can rewrite the denominator as 2 times the absolute value of secant theta. Well, what about dx? How can we transform dx into theta? Well, we're going to calculate the differential. So I'm going to take my equation, x is equal to 2 times the tangent of theta, and I'm going to take the derivative with respect to theta. Right, so this is what I mean by calculate the differential dx, right? Because we're trying to substitute out dx. So once we take the derivative of the left-hand side is dx d theta. If you look at your trig derivative sheet, the derivative for a tangent is secant square. So the derivative with respect to theta for 2 times the tangent of theta would be 2 secant square theta. And now in order to calculate the differential, I'm simply going to multiply both sides by d theta. So dx is equal to 2 secant squared theta d theta. Right, so now we can substitute. I can substitute dx for 2 secant squared theta d theta. I can substitute my denominator, the square root of 4 plus x squared, for 2 times the absolute value of secant theta. So for our second step, we're going to substitute and simplify. So we're going to write this as the integral. So remember, dx is 2 secant square theta d theta our denominator, the square root of 4 plus x squared, we're going to substitute that for 2 times the absolute value of secant theta. We're going to simplify, so the 2's will cancel. The secant in the denominator will cancel one of my secants in the numerator. So this is equal to the integral of secant theta d theta. All right, so just to recap, all right, we're integrating by using a trig substitution. We chose the first triangle on that triangle reference sheet as our reference triangle. We found that x was equal to 2 tangent theta, and that was simply by using the reference triangle. We found that the square root of 4 plus x squared is equal to 2 times the absolute value of secant theta, right? So again, these stem from the reference triangle itself. Then we use a little bit of calculus to find the derivative, to find the differential dx. So we took the derivative with respect to theta. For our first equation, we got dx is equal to 2 secant squared theta d theta. Next, we substituted, right? So we're substituting the variable for a trig equation, which makes this trig substitution. We simplify, and now we are going to integrate. All right, so the third step is to integrate and simplify. So now there's a formula to integrate secant u du. All right, so from our facts, the integral for the secant of u du is the natural log times the absolute value of secant u plus tangent u plus c. So once we integrate, we have the natural log for the secant of theta plus the tangent of theta. And since I don't have any limits of integration, I'm going to add my arbitrary constant. Okay. All right, so we've integrated. Now I'm running into a slight hitch. Notice that my original problem contained the variable x. Once we made our trig substitution and integrated, notice that our variable is now theta. So our last step is to back substitute. And we back substitute using the triangle. All right, so here's what I mean. I have to use my triangle. I have to pull out the secant from the triangle and the tangent. So remember from our relationships, where are they? If I'm looking at the secant, I'm going to take the hypotenuse over the adjacent. If I'm trying to find the tangent, I'm going to take the opposite over the adjacent. So first we're asked to find the secant. So I'm going to take the hypotenuse over the adjacent. So I'm going to take the hypotenuse which is the square root of 4 plus x squared over the adjacent, which is 2. I'm just going to write that out here. So the secant of theta is the square root of 4 plus x squared over 2. I'm also going to write out the tangent. The tangent is the opposite over the adjacent. So the tangent of theta is x over 2. So I'm going to put this all together and write this as the natural log of the absolute value of secant theta, which is the square root of 4 plus x squared over 2 plus the tangent of theta, which is x over 2 plus the arbitrary constant. So notice we have back substituted, and now we are in the original x variable. Okay, so there's 4 steps. The first step is the important one, is to choose a reference triangle. Once you choose a reference triangle, you want to sketch it out and calculate the differential. The next thing we did was substitute and simplify. Then we integrated and simplified. Okay. And lastly, we back substituted. All right, so any questions about this particular example? All right, so notice it dealt with a square root. It dealt with a binomial, which were both perfect squares, and our sign was positive, right? So that represented a hypotenuse. All right, now we'll take a look at, okay, this will be the last example. Okay, this one's kind of long. All right, well, most of these problems in this section are, I should say, tedious. They're kind of involved, right? Especially a problem as we're going to see now. There's going to be some going back and forth between the trig formula sheet and what we're doing to make substitutions. All right, so here we are going to integrate x squared dx divided by the square root of 9 minus x squared. All right, so again, you would go through your usual strategies. You would make a u substitution, which won't work. We can't use integration by parts. We can't use trig, well, we're going to use trig substitutions, but I'm not dealing with specifically any sines or cosines, right? So I can't rewrite anything to try to make any substitutions. So if we look closely at the denominator, notice that this is in the setup as the leg of a right triangle, right? We have 2 terms. The first term is a perfect square, the last term is a perfect square, and we have a minus, right? So from our initial setup with our triangles, notice that if there is a minus, that will represent the length of a leg. Right? So as we're looking at our reference triangles, the last 2 triangles represent the length of legs. Right? So which one would we choose? Well, if we look at our radical, we had 9 minus x squared, right? So the x squared term came last, so we would use the second reference triangle as our reference triangle. All right, so notice I'm basing which triangle I choose. I'm basing that upon what I'm actually given. So I'm given the square root of 9 minus x squared, which fits the second reference triangle setup. So I'm going to sketch that out. So I'm going to sketch this out. So let me write out the steps. We're going to choose a reference triangle. And we're going to calculate the differential dx. Right, so here's our triangle. The length of this leg is going to be 9 minus x squared. My hypotenuse was a. So if a squared is 9, a would equal to 3. And the length of my other leg is x. All right, so this was all based on the second reference angle, the reference triangle. So from the second reference triangle, I can pull out the following facts. X is equal to 3 times the sine of theta, and the square root of 9 minus x squared, that's equal to 3 times the absolute value for cosine of theta. All right, so again, if you look at your second reference triangle setup, these are the facts that follow based on what we're given. So we chose a reference triangle, we sketched it out. Now let's calculate the differential. So again, I'm going to take my x equal to 3 times the sine of theta equation. I'm going to take the derivative with respect to theta for both sides. So on the left-hand side, I have dx d theta. On the right-hand side, if you refer to your trig derivative sheet, the derivative of sine is cosine. So the derivative with respect to theta for 3 times the sine of theta would be 3 times the cosine of theta. Right. So lastly, I'm going to multiply both sides by d theta. So dx is equal to 3 cosine theta d theta. All right, so we've sketched out the reference triangle. We pulled out the facts that follow, and we found dx. So now our second step is to substitute and simplify. Okay, so we have x squared dx. So I can substitute dx for 3 cosine theta d theta. What can I do about x squared? right? How can I transform that into the theta variable? Well, I have this relationship. X is equal to 3 times the sine of theta. So x squared, right? If I square one side, I have to square the other side. X squared would equal to 9 sine squared theta. So I'm going to make my substitution. I'm going to substitute x squared. There should be an equal here. X squared, I'm going to substitute that for 9 times sine squared theta times, I'm going to substitute dx for 3 cosine theta d theta. I'm going to substitute the denominator, the square root of 9 minus x squared. I'm going to substitute that for 3 times the absolute value of cosine theta. Right. And next we're going to simplify. All right, so once again we substituted x squared. Right, we simply squared both sides. We substituted that for 9 times the sine squared theta. We substituted dx for 3 cosine theta d theta, and we substituted the denominator, right, using the facts from the reference triangle. So now if we simplify, okay, and I'm going to pull a 9 in front of the integral operator. We have 9 times the sine square of theta d theta. All right, so now we're going to integrate. So this is our third step, which is to integrate. So keep in mind, we have a fact, we have a formula for the integral of sine square. All right, so if I pull that back out, the integral of sine square is 1/2 u minus 1/4 times the sine of 2u plus c. Or I can write it out in this form. So notice what I'm going to do with this form. I have 1/2. So if I pull that 1/2 in front, I'm going to have 9/2 right? Because I'm multiplying this whole thing by 9 times theta minus the sine of 2 theta over 2 plus the arbitrary constant. All right, so I took our formula, basically multiplied it by 9, right, and changed the u variable to a theta variable. So notice we've integrated it. And let me put another step here. We want to integrate and simplify. Okay, because we didn't necessarily have to simplify in that first example because we got a nice integral, we just got secant. But here we will have to simplify, and we'll see why in a second. All right, but notice that our variable is in the theta and our original variable was x. So we have to back substitute. So now when you back substitute, we're going to use a reference triangle, right? We can find theta. We can actually find theta. And I'm going to use this relationship. X is equal to 3 times the sine of theta. I'm just going to rewrite that here. X is equal to 3 times the sine of theta. I can divide both sides by 3. And I'm going to kind of flip this around. The sine of theta is equal to x over 3. Right, I can divide both sides by 3. And in order to find theta, I can take the arc sine of both sides. So if I take the arc sine of my left-hand side, the arc sine of the sine of theta simply gives me theta. And I have to take the arc sine of my right-hand side, so the arc sine of x over 3 would simply be the arc sine of x over 3, and I have theta. But what about 2 theta? Now in my triangle, I only can find sine and cosine, so I need to try to rewrite the sine of 2 theta in simpler terms. I need to write it as a sine and or cosine. So in order to do that, I'm going to result back to the trig formula sheet. Okay, so just switching back to my desktop screen, I am on the trig formula sheet. And I'm going to look at the double number identities. And notice here I have this double number identity. The double angle for sine is equal to 2 times the sine of A times the cosine of A. And I can actually find the sine and the cosine. So I'm going to make a trig substitution. I'm going to substitute the sine of 2 theta for 2 times the sine of theta times the cosine of theta. All right, so I want you to see where this substitution is coming from. Okay, so I'm going to write this out as 9/2 times theta minus, so remember that the sine of 2 theta was 2 times the sine of theta times the cosine of theta. That's divided by 2. Right, bring down my arbitrary constant. Now my 2's will cancel, and I'm left with 9/2 times theta minus the sine of theta times the cosine of theta. All right, plus the arbitrary constant. All right, so now we can back substitute. Well, we know what theta is, right? Theta is the arc sine of x over 3. We know what sine is. Sine is going to be x over 3. Well, what about cosine? Well, remember from our relationships, the cosine is the adjacent over the hypotenuse. So we can find the cosine of our angle as the adjacent over the hypotenuse. So the cosine of theta That's equal to the adjacent, which is the square root of 9 minus x squared over 3. So if we write all of this out, I'm going to try to do it here. We should have a final solution as 9/2 times the arc sine of x over 3 minus the sine of theta, which is x over 3, times the cosine of theta, which is the square root of 9 minus x squared over 3 plus c and I have another set of parentheses. I'm going to write another step. So we're going to simplify this a little bit. So I'm just going to rewrite that here. So this is equal to 9/2 times the arc sine of x over 3 minus x over 3 times the square root of 9 minus x squared over 3 plus c. Right, I'm going to simplify. I'm going to combine these two. I'm simply going to multiply the denominators. So this is 9/2, which is still on the outside of my set of parentheses, times the arc sine of x over 3 minus x times the square root of 9 minus x squared over 9 plus c. All right, so notice when you multiply fractions, you just multiply the numerators, multiply the denominators, but I can't actually multiply x times anything in the square root. I could just simply write it in a product form. And then if you were to distribute, we have 9/2 times the arc sine of x over 3 minus, and when I distribute 9/2, my 9's will cancel, x times the square root of 9 minus x squared over 2 plus the arbitrary constant. All right, so again, you'll notice how involved this problem was based on the other problem. So I will review this problem. Okay, so let's go back. We were given a triangle, we were given an integral. From that integral, we chose the second triangle on our triangle reference sheet, okay, as our reference triangle. We listed out the given information just based on the triangle. We were able to write out the equation for x. We're also able to write out the equation for 9 minus x squared. We found the differential dx. Right, we use our x equal to equation. We took the derivative with respect to theta for both sides. We then substituted, right? We had to substitute dx. We had to substitute the square root of 9 minus x squared. And we also had to substitute for x squared. Right, so we had everything we needed in that reference triangle. The next thing we did was we substituted, we simplified, we used the fact to integrate this, right? We used the fact that sine square was equal to 1/2 x minus 1/2 sine 2x plus c. Right, we simply multiplied that integral by 9. We then made a trig substitution, right, because we cannot find the sine of 2 theta based on our triangle, right? We can only find the 6 trig functions. So we had to re-express the double angle for sine in terms of sine and cosine. So we made a trig substitution. We used a double angle for sine formula, and we simplified. Next, we used our reference triangle to back substitute, right? So we were able to find theta. We found theta by solving our x equal to equation for theta. So we divided by 3. We took the arc sine of both sides. We were able to find sine. Okay, we took the same x equal to equation, solved it for sine. We were also able to find cosine by using our reference triangle, and we found that to be the square root of 9 minus x squared over 3. Next, we simplified. All right, so with that, I am going to stop the recording.